When evaluating geologic time, there are two ways of looking at ages of geologic material. In this video, we will practice how to determine or calculate absolute ages. So this is where we actually give a number to an age, 70 million years old, 30 million years old, of a geologic material. Now, to do absolute age dates, we are basing it on radioactive decay. So what happens is you have an unstable parent atom. That atom is going to decay into a stable daughter atom. There are known rates of decay depending on what the isotope or what the atom is, the element that it is, and the rate that it will decay into the daughter. So we are going to look at an example based on filling out this table. So half-life is the amount of time it takes for half of the parents present to decay into daughters. So let's start in our hypothetical case with 100 parent atoms and 0 daughter atoms. So all of the atoms are the radioactive parent. None, or 0, have decayed into the daughter when this material is first made, and there are 0 half-lives. The next column is looking at the number of daughter atoms divided by the number of parent. So we take the numbers from the two previous columns. 0 divided by 100. The last column, we are going to have a ratio. And the way that it works is you always have 1 and then a colon, so we can put that for every cell in that column, 1 and then colon. The number that goes on the right of the colon is the number you get from doing this division. So 0 divided by 100 is 0. That is going to go right over here. When we have a half-life again, what we are looking at is half of the parents have decayed to daughters, while half remain parent atoms. So I'm going to make some notes here. So, half of the 100 remain parents, and I'm going to write that number. So half of 100 is 50, while half of the parents get added to what is in the daughter column. So I've made a note here. We're taking half of this number and adding it to the number that's in this cell to get down here. So half of 100 is 50, plus 0 is going to give us 50 daughter atoms. We can then set up our number of daughter divided by our number of parents, and we see 50 is the number in each of these cells, so 50 divided by 50 is 1, which is going to go on the right of the colon here. We then do the same thing for looking at the second half-life. Half of the parents' atoms will remain, so this time we're taking half of 50 and putting it here, which is going to be 25. So we write that into the cell. We then take half of the parents and add them to the number that's already in the daughter column. So we're taking half of the 50, which is 25, adding it to the number that are already there. 25 plus 50 is going to give us 75. We can then set up our division equation. And we have 75, the number of daughters, divided by 25, the number of parents, gives us 3, which we can put on the right of the colon here. One other tip when filling out a table like this to determine parent-to-daughter ratios and the number of half-lives is the number in the parent column and the number in the daughter column should always add up to what you started with. So 50 plus 50 adds up to 100, 25 plus 75 adds up to 100. Let's do a sample problem of what we could calculate an absolute age. So carbon-14 has a half-life of 5,730 years. So that tells you, because this element has a half-life, it is the parent. It is what is going to decay into something else. If you measure a shell with 25% carbon-14 and 75% nitrogen-14, how old is the sample? So again, we know carbon-14 is the parent because it's what has a half-life. That means nitrogen-14 is the daughter. So the first thing we want to do is determine the parent-to-daughter ratio. So we look at figuring out something like we did in this column. The number of daughter, 75%, divided by the number of parent, 25%. So go ahead and write that down. So 75% divided by 25% is going to give us a number of 3. And remember, what we're determining here is what goes on the right of the ratio. So we know that we're looking at a 1:3 parent-to-daughter ratio, and we also know that a 1:3 ratio means there have been 2 half-lives. So make a note of that. So we see 1:3 ratio, 2 half-lives. We're also told the age of each half-life, 5,730 years old. So there have been 2 half-lives. Each one is 5,730 years. We can set up a simple equation where we are taking 2, our number of half-lives, times the amount of time for each half-life, which is 5,730 years. So you can go ahead and plug that into a calculator, and you will get an age of the shell that is 11,460 years old. Now this was a simple example for you. There will be more complex problems that we do, but the idea and the concepts will stay the same. You look at the number of daughters to parents, you figure out the ratio, that tells you how many half-lives it's been, and then you do math to look at how many half-lives have passed, the age of each half-life, to determine how old the material you're evaluating is. So these are the steps in the math that you will be expected to do when performing absolute age calculations in an intro geology geologic time lab.